All right, so today we're going to be looking at force diagrams using everything we know and calculating kind of the different forces involved. So starting off with, down there at the bottom is the first problem we're going to work on today. So a rightward force is applied to a 6 kilogram object. So let me draw that first. All right, that's my object. 6 kilograms. Okay. Rightward force, so force to the right, is applied to a 6 kilogram object to move it across a rough surface at constant velocity. All right. Constant velocity means there's no acceleration. There's no change in acceleration. Okay. So that means acceleration 0. The object encounters 15 newtons of frictional force. So F of friction is equal to 15 newtons. Use the diagram to determine the gravitational force, normal force, net force, and applied force. Neglect air resistance. All right. So we've got here we have the force of gravity. We're just pulling everything down. You know, if we imagine that this box sitting, imagine that's a flat surface. If the box is pushing down on the earth would be pushing back up to it. We call that the normal force. All right, so this is the applied force, or F app. All right, so one of the big things down here, constant velocity. So I know that F net is equal to ma. If there's no change in velocity, there's no acceleration. So it doesn't matter what my mass is, my net force, 6 times 0, that's still 0. Net force is 0. All right. That doesn't mean we're not applying a force to it. It just means that since there's no change in acceleration, we have no net force. All of the force going into it is going into maintaining that velocity, not in changing its acceleration. So in this case, the amount of force that I'm pushing on it, the applied force, has to be equal the amount that friction is pushing the other way. So if this one's 15 newtons in that direction, I could call that negative 15 newtons. That means the amount I'm applying has to be equal, but in the opposite direction. All right, we got 2 of the 4 done. Next one I think that we can work on, we can't find the normal force unless we know the force of gravity. So let's start with that. So force of gravity equals mass times acceleration due to gravity. So in this case we have 6 kilograms. Let's even go negative 9.81 meters per second squared. Can't do that one in my head. So let's go 6 times 9.81. 58.86 is what I'm getting. All right, so force of gravity, the amount going straight down. Let's even go put that there. So I can even fill some of this stuff in over here. All right, so that's how much newtons, that's how much force is pushing down or pulling down on our 6 kilogram mass here. So at 58.86 newtons, that's how much the box is pushing on the floor. That's also how much the floor is pushing up against the box. Just, I guess I could make that negative, doesn't really matter here. That means normal force, 58.86 newtons. And easy enough, right? I mean, we only even had to do math really just some one time for this one. The big thing though is identifying that constant velocity means no acceleration, which means no net force. No acceleration, no net force. All right, so let's go down to number 2. All right, I will even scroll down here. All right, next problem. A rightward force is applied to a 10 kilogram object. All right, so this is going to be pretty familiar. This time though we have a 10 kilogram object. We are on Earth, so let's get force of gravity. A rightward force, so that means I'm applying my force this way. That means the force opposing it is the force of friction. Remember, friction just always opposes whatever direction the applied force is. It doesn't have like a set direction itself. If gravity is pulling down on this object, the floor must be pushing up on it. All right, we're going to look for the exact same things again. So, a rightward force is applied to a 10 kilogram object to move it across a rough surface at constant velocity. All right. Now, though, we're going into something new. They didn't give us the frictional force. That's something we have to calculate here. So, new equation time. The force of friction, sometimes you'll even see it like that. Sometimes you'll see it, it's the whole thing, is equal to that little mu, Greek letter mu. Really what this stands for is the coefficient of friction. That coefficient of friction is different for different surfaces, depends upon the roughness, even at the molecular level. Really, though, the force of friction is just that coefficient times the normal force. However much gravity is pulling down, or pushing up, I should say, um, that increases our friction. So in this case, force of friction, they say that the coefficient of friction is 0.2. Does it have a unit to it? Simply because our normal force is in newtons, force of friction is in newtons as well. So coefficient of friction, no units. All right. Looks like I need to figure out what the normal force is. How much is this box, or how much is the ground pushing up onto the box? So before I do that, I first need to find the force of gravity. This we know is just mass times acceleration due to gravity. All right, so let's see. It's a 10 kilogram box. Oh my, I don't even need a calculator for this one. Times negative 9.81 meters per second squared. Multiply these two together, we should get negative 98.1 newtons. Okay? So force of gravity, negative 98.1 newtons. All right. That means my normal force is the exact same value, just in this case, the opposite sign. So if 98.1 is how much the box is pushing down on the ground, 98.1 newtons is how much the floor is pushing up on the box. All right. Got 2 of the 4 done. Now that I have the normal force, we'll even put it down here. All right, so now I can figure out what this is. So where Fn is here, I need to put 98.1. Used to be able to do that in my head. So let's go 0.2 times 98.1. Looks like I'm going to get 19.62. All right, and that was the force of friction. All right, and in this case, once again, constant velocity means acceleration 0, means our net force is 0. That means our applied has to balance out the friction, so 19.62 newtons. All right, that's those four values there. All right, one more where it's not quite that easy. All right, let's scroll down a little bit more. All right, so in this case, we have a rightward. I mess all this up. All right, let's get our box going on here. 5 kilogram object, a rightward force is applied to our 5 kilogram object. To move it across a rough surface with a rightward acceleration of 2 meters per second or 2 meters per second squared. So acceleration, I'm going to even say that was positive. All right, so in this case, my applied force and my frictional force will not cancel out. All right, so let's get all 4 of the things down I need. All right, so other thing I'm going to need to find is net force. But we'll come back to that. Actually, we can do net force first. So net force equals mass times acceleration. So in this case, the mass we said was 5 kilograms. So in this case, we're looking at the horizontal, the x direction, if you will, times 9.81 meters per second squared. I should really have that one memorized at some point. For 9.05 newtons. Just put that there, just so I don't have to add another arrow there. All right. We know in this case, force of gravity is equal to the net force. So let's figure out force of gravity. We have 5. Oh, wait, I messed up already. That's not F net. That's force of gravity. Because mass times acceleration due to gravity isn't net force. That's force of gravity. No, that was not intentional either. I wish I could claim that it was. All right. Now let's find the net force. So we still have mass, 5 kilograms. But in this case, the net force we said was 2 meters per second squared for the acceleration to the right times 2. That should give me 10 newtons. All right, that's my net force. All right, that'll be important here in a bit. All right, force of gravity, though, we already found 49.05 newtons downward. That means our normal force is 49.05 newtons upward. Now, using our new equation, we have the force of friction is equal to mass. Nope, not mass. Is equal to the coefficient of friction times the normal force. In this case, they say that the coefficient of friction is 0.1, so it's a smoother surface than what we worked with last time. Force normal for 9.05. Even if I considered, okay, so that's pushing up. This time I just need to move my decimal, so we're down to 4.905 newtons. All right, that's my force of friction. My net force, though, F net, should be equal to my applied force minus the force of friction. So F net, kind of in that horizontal direction, should equal the applied minus force of friction. So in this case, the net force we found, if this box is moving with an acceleration of 2 meters per second squared sideways, that means the force net, 10 newtons, is equal to the applied force minus the force of friction we just found was 4.905 newtons. Now it's just basic algebra to get applied force by itself. Add 4.905 to both sides, and we should get 14.905. All right, so that one was a little bit trickier. That's still just doing the things that we've been doing. Uh, two things to note here is not that, um, but force of friction, if I need to calculate it, it's just the normal force times coefficient of friction, which will be given to you in the problem if you need it. The other thing is net force is the sum of all of the forces together. So if I had made this a negative, then I would have made that a positive, and that would have been something like that. Really, it just works out to be applied force minus the force of friction. So then I just work backwards. Other than that, the big thing though is drawing these, because this is great when we're looking at horizontal surfaces. Everything's easy and straightforward, especially this whole force of gravity equaling the normal force. That gets really tricky with what we do next, which is when we put these things on angles, put these things on inclined planes. I'd say that's probably a long enough video, so good luck. Oh wait, one more thing. This is going to be a longer video. Oh, where was I? Let's go. All right, so let's look at this quick. So, diagrams there. Yay, diagrams. There we go. Let's just look at this one right here. So they give us a box. No, I'll figure this out at some point. All right. So they give us a box. Now they're doing their arrows a little bit differently. In this case, they put the normal force up here. This would be the force of friction. This is the force of gravity. They tell us that's 200 newtons. And 50 newtons. So this will be like the applied force. They tell us that the net force is 0. So I'm looking at the first one right here. With the net force being 0, that means my up and downs need to equal each other and my sides to sides need to equal each other. So in this case, if I have 200 newtons coming down, I have to have 200 newtons going up. If I have 50 newtons coming out the side, I need 50 newtons coming out the other side. That's pretty easy. For this next picture, box, diagram going up, going down. In this case, we say if gravity's pulling down 200 newtons, but we have a net force of 900 newtons in the upward direction. Remember, net force is going to be when we add these things together, or in this case, subtract these two since they're going in opposite directions. So really, if F net, let's even just call this I'm going to call it the normal force. It could be the applied force. Really, it's just going to be Fn minus, and if we say this is Fg, minus Fg. So in this case, F net is equal to Fn minus 200 newtons. We know the net force is 900. So now to get Fn by itself, we just add 200 both sides. We should get 1,100 newtons. All right, other than that, practice problems and good luck.